the next speaker is Nguyen from RIKEN-AIP. He will be talking about statistical inference for neural network-based image segmentation.
Okay, thank you. Hi everyone. So my name is Duy. So I'm currently a postdoc in data-driven biomedical science team. So today I'm going to talk about. Do you know how to hide the thumbnail?
No, just change it.
Yeah.
Swipe the mouse a little bit.
Okay. Yeah, thank you. Yeah. So today I'm going to talk about like statistical inference for the neural network-based image segmentation problem. So it's kind of like a reliability quantification for the segmentation result obtained from deep neural network. So first, I'm going to introduce a little bit about, briefly revise about the image segmentation. Then I'm going to talk about the reliability issue in this problem, and I'm going to discuss the method that to resolve the problem. So yeah, so you already know that image segmentation is a very fundamental task in computer vision, and in the literature there are several kind of methods have been proposed, like clustering or like graph cut or something image segmentation. But recently, like DNN-based image segment has performed like remarkable performance. So that's why we usually like use DNN for this kind of task. So the most popular one is UNet or SegNet. Yeah, but the issue is that even this state-of-the-art neural networks are usually used, so it's achieve high accuracy. But if we focus on the metrics of like controlling the type 1 error or the false alarm rate, so this kind of network also like cannot control the probability of obtaining the false detection. For example, like even the input brain image without any tumor. So if we input this image to the deep neural network, we still obtain some object and background, even though this is the picture of the normal people, no disease or no tumor. So this indicates that if we just use the result obtained from DNA, so it might be unreliable and harmful. So for the medical diagnosis, so which means that we need a method or a metric to quantify the uncertainty of the result obtained from the deep neural network. So this is the reliability, quantify the reliability with hypothesis testing. So in general, for the uncertainty quantification, we have several criteria: robustness, statistical, or fairness, or something. And in this talk, I'm going to focus on the statistical direction for quantify the uncertainty of the uncertainty. So in the framework of statistics, so hypothesis testing is a popular framework for the reliability evaluation. So this is the like general concept of hypothesis testing. So first we input the image to the deep machine learning algorithm for here the DNN, and we obtain the object and the background. And these are the general steps of the hypothesis testing framework. So first we need to define the question that we want to test. So the question here is that whether this object is actually a tumor or not. And then to test this question, we need to define a quantity. So this is called the test statistic. So this test statistic indicate what is the difference, the degree of the difference between the object and background. And then to quantify the largeness of this quantity of this test statistic, we're gonna use the p-value. So p-value is used to quantify whether this delta is large enough or it's just large because we add some noise. And actually, there is no difference between the object and the background. And then finally, at step 4, if the p-value is smaller than some significance level alpha, for example, usually we use 0.05, then we're going to say that this delta, this test statistic is large enough. So which may indicate that, so this indicates that the difference between the object and the background is significant. And we're going to conclude that this is actually the actually true brain tumor that we're going to detect by the true brain tumor in the image. Yeah, so there are some like assisting method. So like in like there are some like for introduction, this is the traditional method for computer p-value. But in the traditional way, we need some knowledge from the expert. So which means that the expert must annotate and must like specify which is the object and which is the background in advance. So if we obtain the object and the background result from the data and from machine learning algorithm, then the traditional p-value is no longer like reliable. And then the second one is the multiple testing correction. So for example, we won't fit any correction. But the major limitation of this multiple testing correction is that we need to like enumerate all possible like segmentation results obtained from the deep neural network. So like, but you know, like this is like unrealistic because we don't know like a lot of possible like possible combination can be generated from the machine learning algorithm. So the main contribution that we're going to propose a practical and inference that can compute a valid p-value or exact p-value to quantify the reliability of the segmentation obtained from DNN, and we're gonna store all the drawback, the limitation of this current method. So this is an example of the proposed method. Yeah, so even we input the image without any tumor to the DNN, and then we obtain the segmentation result. And here is the traditional p-value. So even in the image, there is no actually there is no true tumor exists, but the p-value still is the naive p-value still is very small. So which indicate that the naive p-value is unreliable, because that if the p-value is small, we're gonna say that this is the true tumor region, but actually it's not, because this is the image of there is no true tumor region exist in this image. But if we use the proposed p-value, the p-value is large. Large means that this p-value greater than the significance level alpha 0.5. So which means that we say that this result is actually obtained because of the image is corrupted by noise, and there are no actually tumor region exist in this image. So which means that with the proposed method, with the proposed p-value, we can successfully like identify the false detection obtained from the DNN. So actually, I would say that this in the proposed method is also not perfect. So we the goal is that with the proposed method, we still mistakenly identify something. But the advantage is that we can control the fonts. With the naive p-value, we cannot control the font, but with the proposed method, we can control, for example, 5%. We can control up about the probability of obtaining the incorrectness of the machine of the result obtained from machine learning algorithm.
So was the naive p-value computed from the original image or output of the image?
The p-value computed from the original image.
What about the proposed method?
Yeah, the proposed method also. Yeah. So this is the more. So that now I'm going to talk about more about the problem setup. So now the image is represented n-dimensional vector in the n-dimensional space. So this is the random image, and this random image is corrupted by the noise. So here I assume that this is the Gaussian noise. So this is the true signal, and epsilon is the noise. And after we obtain the image, we're gonna input the image into the machine learning algorithm. So for example, here algorithm can be the DNN or any algorithm, and we input the image into the algorithm, and we obtain the object region and background region. So this is the set of the pixel assigned to the object, and this is the set of pixel assigned to the background. And then after obtaining the segmentation result, we're gonna define the hypothesis testing. So we want to test whether the background is actually different from the object or not. So this is the hypothesis that I want to test. We want to test whether the average mean pixel in the object equal the average mean in the background or not. So this is the question that we need to test and answer. And then to test this question, we're gonna define the test statistic. So here, the test statistic is the difference between the object and background. Here we just check the average mean pixel in the object and minus the average mean pixel in the background. And the point is that here, this test statistic, this quantity can be represented as a linear contract with respect to the data. So eta transpose x. And here you say that here eta is the vector indicate that which element belong to the object and which element belong to the background. And because that the result the segmentation result we obtain based on from the data, therefore this vector eta is random. It's a random variable. And here is x is also a random variable. So to compute the p-value, we need to derive the exact. We need to have understand about the distribution of this test statistic, but it's going to be very complicated because both quantities are random. So characterization of deriving the distribution of this test is like complicated. So I'm going to propose the method to like explicitly characterize the distribution of the test statistic by conditioning. So here so we consider the distribution of the test statistic conditional on the segmentation event. So here, if we do so, this concept is like inspired by selective inference framework from Liet on 2016. So the main concept is that because that the eta constructed from the data. So eta is random. So if we conditioning on the event that the segmentation result is obtained, then eta is considered to be fixed. So after conditioning, eta is considered to be fixed. Then the remaining quantum random quantity is x. Then we gonna then the distribution, the conditional distribution can be like characterizable. So we can derive the distribution. So in other words, this distribution is a truncated Gaussian distribution because here we assume that x is corrupted from the Gaussian noise. So this is the follow the truncated Gaussian distribution. So then after we so the remaining that is how can we characterize this conditional data space. So this is just how we can define this space in the and then this is the illustration of the conditional data space. So here we have this is the whole space, and here this set of so we want to identify the space in which when we apply the deep learning algorithm on the any data point in that space, we're gonna obtain the same segmentation result with the observer. So here for this data point, when we derive when we apply the DNN on this data point, we obtain this segmentation result, but it is different from the result when we apply on the observed data. So which means that we're not going to select this data point. And similar here, we're not going to select this data point. But for the blue data point, when we apply DNN on this blue data point, we obtain the same segmentation result as the observed data. So therefore we're going to select this region. And the union of this region is the represented as a conditional data space in this space. Yeah, so which means after if we can explicitly characterize this data space, we can derive the exact distribution of the test statistic, and then the computation of p-value is tractable. Yeah, so this is the main concept. Yeah, so why do we need to conditioning? So conditioning. So it's like the concept of conditioning is make some thing complicated become more simple. Like the conditioning means that we want to make some random quantity become to be fixed. So in other words, like by conditioning on the event that we obtain the object and background from the DNN, then the eta is considered to be fixed, and then the conditional distribution is the truncated Gaussian distribution, and is the truncated Gaussian distribution. Then so this is the remaining task is to how can we efficiently identify this conditional data space because it's complicated. So this is an example, simple example of the how can we identify the conditional data space when we just use the simple threshold-based image segmentation. So if we consider the simple threshold-based image segmentation with the threshold tau, then if the pixel value greater than tau, we're going to assign that pixel to the object. And if the pixel value is smaller than tau, then we're going to assign it to the background. And then the conditional data space can be simply represented as a set of linear inequality. So this set of linear inequality can be represented as a single polyhedron in the data space. So this is how can we characterize the conditional data space with a simple segmentation algorithm. But like in the case of deep neural network, it's more challenging because in the case of deep neural network, the conditional data space is complicated and it's not like simply represented an intersection of linear inequality. In other words, it's kind of union of multiple polyhedron. So that's why we're gonna propose an approach to efficiently identify the conditional data space in the case of DNN by considering a class of piecewise linear network. So piecewise linear network, it means that all the operation on all the activation function we use in the network can be represented as a piecewise linear function. Yeah, so by focusing on the class of piecewise linear network, then the conditional data space can be represented as a union of polyhedron in the data space. So here we propose a two iterative steps. So at the step A, we can see a single polyhedron by additionally conditioning on all the activeness of the hidden layer of the hidden node or the DNN. So in other words, by not only conditioning on the segmentation event, but if we conditioning on the activeness of all the activation function in the network, then we can represent it, the selection event as a single polyhedron. And then by combining multiple polyhedron, by combining multiple step A, then we're gonna derive, we're gonna obtain the union of polyhedron that have the same segmentation result as the observed data. So for example, like he more said, with starting from the left, and then we for example, we have this data point, and we obtain the DNN, apply the DNN on this data point, and we obtain this segmentation result. And by considering this segmentation result and this activeness of the hidden layer function, we can characterize this polyhedron. But actually, this segmentation result is different from the result we obtain from the observed data. Then we're gonna skip and we do not select in this region. And then we jump to the data point in this space. And then we apply DNN again. So we apply DNN again, and we, by considering this activeness of the ReLU function, we can characterize this single polyhedron. And by in this single polyhedron, we obtain the same segmentation result with the observed data. Then we're gonna select this region, and gradually, step by step, from to the right, we're gonna obtain this region. But the segmentation result is different. Then we skip, and then for this reason, the segmentation result is the same with the observed data. Then we're gonna select this region, and gradually, finally, we go to the right. And after that, we just take the union of the polyhedron. So in which, when we apply the DNN on every data point in that region, we obtain the same segmentation result as the observed data. And now we already identify the conditional data space. Then the computation of p-value is like straightforward, like by considering the.
Why does the region become polyhedron? I didn't
know. Because that we assume that because we consider the piecewise linear network, then all the operation can be represented.
Network is piecewise
Yes. Then that's why we can.
That's not the feature space, but original data.
Original space. Because the piecewise linear, then the operation of the neuron can be characterized by a set of linear inequality. That's why we have the polyhedron. So by using this feature, so this concept is related to the parametric programming concept, so we can efficiently identify. So this concept parametric is similar to the regularization path in lasso. So by focus on the direction of the statistic, the direction of interest, we can efficiently identify the subspace that we are interested in. So this is the concept of parametric programming. So we can efficiently identify this number of polyhedron. So actually, in the worst case, the number of polyhedron can be like exponentially increased. So the complexity in the worst case still like in exponential order. But actually, in the practice, we usually observe that the number of polyhedron is just linear increase with respect to the size of the data set. So it's similar in the case of like regularization path in the lasso. So this is a more detail of the step one. So as I already told you, that by considering all activeness of the hidden nodes in the DNN ReLU can be characterized as a linear inequality. Max pooling can be also characterized as a linear inequality, and threshold or convolution can be characterized as a linear inequality. Then, by consider all this kind of operation, we can have the set of linear inequality, and this set can be represented as a polyhedron in the original data space. And by combining multiple steps, by combining multiple polyhedron, we can identify the conditional data space that we want to define. So this is the summary of the whole algorithm. So first, given the observed data, we have the observed image. We apply the DNN on the observed image and obtain the observed segmentation result. So observed object and observed background. Then at the second step, we're gonna use the proposed method, parametric programming, to identify the conditional data space. So the conditional data space here is the space where we obtain the same segmentation result as the observed data. And then after obtain the conditional data space, we're gonna compute the conditional p-value. So for example, if we just consider the naive p-value, we don't consider this conditioning. So that's why it's invalid. But by conditioning on the conditional data space, then this p-value is valid in the sense that we can successfully controlling the type 1 error or the probability of identify false detection. And then if the p-value is more than alpha, we're gonna say that there exists some object in the input image. Otherwise, we cannot say that. And the result is not statistical significant. So this is the summarization of the whole algorithm. This is some experimental result. So the first is the case of the false positive image example. So we consider like in the input image contain no like tumor region, but you can see that the naive p-value is still very small. It's like almost 0. so which indicate that the traditional p-value is unreliable. But with the proposed p-value, which is large is greater than 0.05, so which means that we say that this result obtained from DNN is just because of the noise, and there actually no tumor region exists in the image. So which means with the proposed p-value, we can successfully identify the incorrectness result obtained from the DNN for segmentation task. And then by consider the second is for the true positive example, so where the image contains true tumor region, then both the naive p-value and the proposed p-value is small, so we indicate that there actually exist true tumor region in the image. Yeah, so in summary, so by using the proposed method, we can successfully identify the false detection of the DNN and can also identify the true correction of DNN, and we can control the probability of obtaining the false detection under some level. For example, 5% we obtain the false correction. So which means that we can control the uncertainty of the machine learning algorithm by using the proposed p-value. Yeah, thank you so much for listening. Yeah. Yeah.
So because you give a condition,
yeah,
then the p-value always increase?
No, actually, the p-value under the null hypothesis is uniformly distributed. Yeah, so like under the null hypothesis, the distribution of the p-value is uniform. So which means that we can always control the type 1 error for any alpha from 0 to 1. Yeah.
And so second question is, can you also consider like a numerical approach, like a permutation test?
Okay, so in the case of permutation set, we need to require that the pixel is like independent. But for example, in the case of image, pixel usually correlated. So if we permute, we broke the structure of the image. So which means that if we broken the structure of the image, then we're gonna fail to control the FBR.
Can you somehow cleverly done by swapping patches of images or something?
Yeah. Actually, we can swap. But for example, when I try to swap something, empirically I fail to control the FBR. Yeah. And actually, there is no theory to guarantee the control. Yeah.
Okay. Other questions?
Sorry, maybe you explained in the beginning, but is it essential to apply it for segmentation models, or can it be applicable to like other? I'm not really sure, but classification models or detection models.
Yeah. So my method is like in general, if the network is piecewise linear and the test statistic is linear, then it's applicable. So the general requirement is that piecewise linear network and linear test statistic or quadratic test statistic, then the method is applicable. That's in general picture.
Okay, thank you very much.
Can you say a few words on the computational complexity?
Okay.
So you need to sort of parametric.
Exactly. So in the worst case, so of course in the worst case, the computational is like the number of polytope is exponentially increasing. So it's in the worst case, and yeah, that is the fact. And I must admit that. But in practical, so usually the number of polytope is linearly increasing with respect to the size of the data. So the concept is linear to the case of Lasso regularization path. So when we change the lambda, the reason is linear increasing in practice, but in general, the complexity is exponential.
Other questions?
How can I define or find that parameterized line?
So like for example, like after you obtain the segmentation result, then you're gonna compute the test statistic. Here is the eta, and by projecting the data to this direction, you have the line. Yeah, eta is the vector, and you project the data to this vector, is a line in the data. Yeah.
Okay, thank you.
Thank you very much.
All right, shall we have lunch then? Okay, thank you very much.
Okay.